Hello, this video includes information on titrations and indicators.
We have a solution down here and we have a solution up in our burette, and we're going to add the solution from the burette to the solution in the flask. And we have 2 points that are important. The first point is called the equivalence point. And when we deal with the equivalence point, it's essentially the stoichiometric equivalence point. Okay, it's where the moles of acid completely neutralize the moles of base. The end point is something that we measure in lab with an indicator. And it's measured by a color change that indicator goes through. And what we want is to have the end point, the color change, to be as close to the equivalence point, the stoichiometric equivalence point, as possible, so that this color change takes place when the moles of acid equal the moles of base. So let's look at titration curves. And a titration curve is some kind of a curve that takes a property of a solution and plots it versus the amount of added titrant, the amount of liquid that comes out of the burette and drains into the flask. And when we talk about acid-base titrations, we typically have pH as the property we're measuring. So here's an example of a strong acid, strong base titration curve. So if we look along the x-axis, we're talking about the volume of 0.100 molar sodium hydroxide that's added to our acid. So at the beginning, we don't have any base added yet, so we just have acid. And what we do is we measure how the pH changes as we add sodium hydroxide. So as we add sodium hydroxide, we can trace that change in pH. And a classic part of a titration curve is this part right in along here. Because right here is where we have our equivalence point. So this is the point where the moles of the strong acid equal the moles of the strong base. And we also have in here some indicators. And indicators change color at different pH ranges. Their endpoints are different. So methyl red, okay, changes colors around 4 or 5 for the pH. Bromethymol blue tends to change colors between like 6 and 8. And phenolphthalein is an indicator that changes colors between like 8 and 10. Now, this is a very similar titration curve. The only difference is we're looking at a weak acid being titrated with a strong base. So along the x-axis again, how much sodium hydroxide are we adding? And along the y-axis, we have our pH. So here is where we start with just weak acid in the solution. And notice that the pH of the weak acid is higher than over here, the pH of the strong acid. And that makes sense because strong acids 100% dissociate, so they have more hydrogen ions in them than weak acids do because they only partially dissociate. So as we add the strong base to this weak acid, we're going to notice that the pH goes up. It's a little bit of a different curve look here than here. But we also have this characteristic, very steep change in pH here. And again, our equivalence point would be here. Okay, general look of what titration curves look like. So now we're going to do some math calculations. Okay, and they're going to be very familiar kinds of calculations. So talking about titrations is almost a good way to wrap up the chapter on acids and bases. So for this example, we have 0.100 molar sodium hydroxide. And we're going to titrate it with titrate it into 50 milliliters of 0.100 molar hydrochloric acid. So this is what we're starting with in our flask. 50 milliliters of 0.100 molar hydrochloric acid. And what we want to do is we want to calculate what the pH will be before we add any sodium hydroxide. And then after we add 40 milliliters of our sodium hydroxide, and then after we add 50 milliliters of our sodium hydroxide, and then after we add 50.2 milliliters of sodium hydroxide. So we're going to look at the titration at 4 places during that titration. Let's look at A first. Actually, let's look at the reaction first. So we have HCl. Okay, there's our hydrochloric acid. We're reacting it with sodium hydroxide. Okay, there's our base. It's a double displacement reaction. We're going to produce sodium chloride and water as our product. Now, strong acids and strong bases react to completion. So there's no equilibrium here. Okay, the arrow goes in one direction, which means we're going to be looking at a limiting reactant problem. And the sodium chloride that we produce is a salt. It's also a neutral salt. So what that means is the sodium ions and the chloride ions are going to be spectators. So really, when we look at a strong acid, strong base titration, it's the hydrogen ions from the strong acid reacting with the hydroxide ions from the strong base to produce water. And we can write it this way, or we can write it this way, because we know that the hydrogen ions really don't hang out by themselves. They tend to attach to water molecules and form hydronium. They're almost interchangeable. This is kind of the shorthand way of writing it. This is really more true to what you would have in the solution. So we've got hydronium ions reacting with hydroxide ions to produce water. And again, we're going to look before the reaction starts. So that's this point here. After we add 40 milliliters of sodium hydroxide, after we add 50 milliliters of sodium hydroxide, and then after we add, and it's not really on here, but after, oh, here it is. After we add 50.2 milliliters of sodium hydroxide. So let's take a look at the math. When we look at A is really just what's the pH of a strong acid. There's no reaction involved. This is the only thing that's in the solution. So since it's a strong acid, the concentration of the acid equals the concentration of the hydronium ion. So the hydronium ion is 0.100 molar. Well, if we know what the hydronium ion is, we can calculate the pH of the solution. So before we start our titration, the pH of the solution is 1.000. It's this point right here. Now, let's add some sodium hydroxide. So after we add 40 milliliters of sodium hydroxide, what happens to the pH? Well, the first thing we would do is we would write our reaction. Okay, again, you can just write the hydrogen ion here and just put 1 water over here, or you can write it like this. It doesn't really matter. Now, we need to calculate the moles of our acid and our base. They don't start out in the same solution, so we can't just look at their molarities. They're not relative to each other. So we would take the volume and the molarity of our acid and figure out the moles of our acid. So we have 5.00 times 10 to the minus 3 moles of hydronium ion in our solution. Again, we're just taking molarity times volume. That gives us moles. And this number is going to be the same throughout the titration because we're not changing the amount of hydrochloric acid. that we have in our solution. But let's look at the hydroxide. Now, originally we didn't have any hydroxide, but now we've added 40 milliliters of 0.100 molar. Well, you have to convert milliliters to liters. And then taking the molarity times the volume gives us the moles of our hydroxide ion. So we have 4.00 times 10 to the minus 3 moles of hydroxide ion. Now, strong acids and strong bases react to completion. So when we look at the number of moles of acid we have and the number of moles of base we have, the one that's the smaller one is the limiting reactant. That means the hydroxide is going to be completely consumed. And since it's a 1-to-1 ratio, 4.00 times 10 to the minus 3 moles of this original amount is going to react, and we're going to have some left over. So once the reaction is done, there's no hydroxide left in the solution. It was reacted with the acid. Some of the acid reacted, but there's going to be some acid left over. Well, what we need to do then is calculate the pH of this new solution. We can calculate the concentration, the molarity of the hydronium ion, and then we can calculate the pH of the solution. Now, how do we calculate the molarity? Well, it's moles over liters. Here's the number of moles of hydronium that didn't react because the hydroxide ran out. But the volume is the total volume in the container. It was 50 milliliters, but we added 40 milliliters of base. So the new volume is 90 milliliters or 0.0900 liters. Okay, so we're adding the volumes together in order to calculate the molarity of our hydronium ion. Now, once we know what the molarity of the hydronium ion is in the solution, and we take the negative log of this number, that's going to give us the pH. So the negative log of 1.11 times 10 to the minus 2 gives us the pH. Now the pH went up a little bit. Now let's look at point C. We're going to add a little bit more sodium hydroxide. And we're going to do the same process. So we have our reaction. The amount of hydronium ion isn't going to change because we're not adding any more hydronium ion to our container. But the amount of hydroxide is going to change because now we've added 50 milliliters instead of just 40 milliliters. So look at what we have here. We have the same number of moles of acid and base. We're at the equivalence point or the stoichiometric equivalence point. That means we don't have any hydronium ion and we don't have any hydroxide ion from the hydrochloric acid and the sodium hydroxide left in the container. But what we do have is water. And we know that pure water has an equal hydronium to hydroxide ion concentration. And we know that that value is 1 times 10 to the minus 7. Take the negative log of that. The pH at the equivalence point is 7. And as long as we're looking at a strong acid, strong base titration, the pH will always be 7 at the stoichiometric equivalence point. Now, let's look at D. Now we're going to add a little bit more base. We have the same reaction. The amount of acid doesn't change. So we've got 5.00 times 10 to the minus 3 moles of hydronium ion. But now look at how much hydroxide we have. Now the hydroxide becomes in excess. Not by a lot, but a little bit. All of the hydronium is going to react. We're not going to have any of it left over. It's the limiting reactant. We're going to have a little bit of hydroxide left. If we want to calculate the pH of the solution, we're going to figure out the molarity of the hydroxide ion that's left in the solution. From that, we can figure out the pOH, and then we can figure out the pH. But we have to remember again that the volume is the total volume in the container. And we had 50 milliliters of original acid in the flask. And we've added 50.2 milliliters of base. So the new volume is 100.2 milliliters or 0.100 liters, which enables us to calculate the concentration. Now, the first two calculations we did, the molarity was for the hydronium ion because that was what was in excess. But this time, it's the molarity of the hydroxide ion. So if we take the negative log of that molarity, that's going to give us the pOH. If we subtract it from 14, then that'll give us the pH. So what we did is we looked at that titration curve in 4 different places, and the calculations that we've done here match up with those 4 places on the titration curve. If you're looking at a strong acid, strong base titration, this is the reaction you want to deal with. You have to figure out the moles of the acid and the moles of the base, decide what's in excess, figure out the molarity of the excess, and then from there you can calculate the pH of the solution. So let's look at the other scenario that we had on our graph. Okay, now we've got a weak acid and a strong base titration. So we've got 0.100 molar sodium hydroxide that we're adding to 50 milliliters of 0.100 molar acetic acid. Well, acetic acid is a weak acid, so what we're going to be doing is slightly different than what we did before. And we want to calculate what the pH is at various points in the titration. Okay, we're going to figure out what the molarity is before the titration starts, what it is after we add 40 milliliters, what it is after we add 50 milliliters, and 50.2 milliliters. Before we add any titrant, this is what we have in the solution, but acetic acid is a weak acid. Since it's a weak acid, we're going to have an equilibrium that's going to be established. So we've got our acetic acid reacting with water. We're producing acetate and hydronium. We start out with 0.100 acetic acid, but it doesn't all react. Only a little bit of it does. So we're going to have conjugate base and hydronium left in the solution. We can write a K expression. Products over reactants. The Ka for acetic acid is a constant. You just look it up on a table. So 1.80 times 10 to the minus 5 equals x squared over 0.100. So from here, let's see if you can roll this out on your own. Do the math to solve for x. When you solve for x, x is the hydronium ion. Once you know the hydronium ion, you can calculate the pH before we start our titration. Okay, so I'm getting a hydronium ion concentration of 1.34 times 10 to the minus 3. I'm multiplying by 0.1 and taking the square root. And then from there, I just take the negative log of that, and that gives you my pH. Now remember that since I've got 3 significant digits, I want 3 decimal places in my pH. Good. All right. So we haven't started our titration yet, and here's our pH. And notice that the pH of the weak acid was higher than the pH of the strong acid, because the strong acid would have more hydronium ions in it because it 100% dissociates. The weak acid has less hydronium ions in it because only a small percentage of it dissociates. All right, so let's look at the next step. We're going to look after we add 40 milliliters of sodium hydroxide. Okay, well, here's our reaction. The sodium hydroxide is going to react with the acetic acid. Okay, remember that acids give up their hydrogen ion to bases. So we're going to produce acetate ions and water. Strong bases react to completion. So we have the arrow in one direction. So we have to figure out what our limiting reactant is. Now, the acetic acid was in one solution and the sodium hydroxide was in another solution. So we can't compare them with respect to molarities because they're in different volumes. We have to figure out moles. So for the acetic acid, 50 milliliters of 0.100 molar, we have 5.00 times 10 to the minus 3 moles of acetic acid. For the hydroxide, we have 40 milliliters of 0.100. That gives us 4.00 times 10 to the minus 3. All right. So now we need to look at the moles of acid and the moles of base and decide what our limiting reactant is. It's the smaller one. So the hydroxide is the limiting reactant. It's all going to react. The same amount of acid is going to react. What's left over? So all of the base reacts. We've got 1.00 times 10 to the minus 3 moles of acetic acid. All we're doing is taking the 5.00 times 10 to the minus 3 moles that we started with, and we're subtracting 4.00 times 10 to the minus 3 because that's how much of it reacts. This is how much is left over. But we're going to produce acetate as well. Now, let's think about that. We have acetic acid and acetate in the solution. That means this is actually a buffer. Since it's a buffer, we can use the Henderson-Hasselbalch equation and calculate the pH. So the Ka for acetic acid is 1.8 times 10 to the minus 5. We can find the pKa, and we're going to add to that the base over the acid. This is the base, the acetate. This is the acid, the acetic acid. So the negative log of 1.8 times 10 to the minus 5 gives us the pKa. We're going to add to that the log of 4 times 10 to the minus 3 divided by 1 times 10 to the minus 3. And our pH has gone up to 5.347. We've added some base. It's consumed some of the acid and the pH has gone up. We don't have to calculate the molarities. And the reason is the base is in the same solution as the acid is. That means the volume is going to cancel out anyway. So it doesn't matter. We can just put the moles of base over the moles of acid, and it's a shorthand since we don't have to calculate the molarities. Now, that was this point right here. This point on the graph is actually what's called the buffer region or the buffer zone. And anytime we have a weak acid being titrated with a strong base, there's always going to be a region where the pH really doesn't change much at all. And that's because during this point, there will be acid and conjugate base in the solution. There'll be a buffer, the buffer region. So we calculated the pH here. We calculated the pH here. Now let's look at C. Same reaction. We're adding our base to the acid. We're producing acetic acid or acetate and water. Again, we want to figure out the moles. Well, the moles of the acid aren't changing. Okay, we're not adding acid when we titrate, we're adding base. Now we have 50 milliliters of base. We can calculate how many moles of base we have. Okay, the arrow is going in one direction because it's going to react to completion. And if we look, the moles of acid now equal the moles of base. We're at the stoichiometric equivalence point. That means none of the acid will be left and none of the base will be left. But we're going to be producing acetate ions. It's a 1:1:1 ratio. So we're going to have 5.00 times 10 to the minus 3 moles of acetate. Okay, well, we can't figure out the pH from this number. We can only figure out the pH if we know the hydronium ion and the hydroxide ion. So we're going to have to take this another step and think about what this acetate will do in water. Well, the acetate will react with the water. In this case, the water is going to act like the acid, so the hydrogen ion is going to go in this direction. We're going to produce acetic acid and hydroxide. Well, now we have something in solution that's going to enable us to calculate the pH because we've got the hydroxide. So we're looking at essentially a weak base equilibrium. Okay, we've got 5.00 times 10 to the minus 3 moles of acetate ion. We had 50 milliliters of acid mixed with 50 milliliters of base. So we have 100 milliliters or 0.100 liters. So the molarity of our base is 5.00 times 10 to the minus 2. Since it's a weak base, only a little bit of it reacts, X and X. Now, we can calculate X. We know hydroxide then. We can calculate the POH, and then we can calculate the pH. In the previous question, we were given the Ka for acetic acid. But we're looking at a base now. Since we're looking at a base, we need Kb. And Kb is calculated by taking Kw and dividing it by Ka. So we've got our Kb that will equal the concentration of the products over the concentration of the reactants. So 5.6 times 10 to the minus 10 will equal X squared over 0.500 minus 2. See if you can calculate the pH from that. Think about when you calculate X, what X means, and figure out what the pH of the solution will be. 5.3 times 10 to the minus 6 is the hydroxide. So 5.276 is the POH. That means 8.724 is the pH. 3 significant digits means 3 decimal places. So now, and this would be the equivalence point. Now let's go beyond the equivalence point. So our reaction is the same. The moles of acid are the same, but the moles of base have gone up because now we're past the equivalence point. That means the hydroxide is the limiting reactant, or sorry, is the excess reactant. The acid is the limiting reactant. So all of the acid is going to be reacted. Most of the base is going to be reacted, but we're going to have a little bit left over. We're also going to have some acetate ion, okay? Because this is going to be 5.00 times 10 to the minus 3 reacts. 5.00 times 10 to the minus 3 reacts. 5.00 times 10 to the minus 3 is produced. Now, this is a base. This is a weak base. We're going to get so much more from here, all of it, than we are from here. We're going to get just a small amount of hydroxide from our weak base that we're just going to ignore it. It's going to be insignificant. That means these are the moles of the hydroxide ion. We can calculate the molarity of the hydroxide ion. Moles divided by the total volume. So 50 milliliters plus 50.2 milliliters gives us 100.2 milliliters or 0.1002 liters. So this is the concentration of hydroxide. We can calculate the pH because we have the concentration of hydroxide. Calculate what the pH will be at this last point in our titration. All right, so POH is 3.699. pH is 10.301. So let's look at kind of the opposite titration. We're going to look at a weak base being titrated with a strong acid. So now the x-axis here is the volume of hydrochloric acid that's added. That means we're going to start with the weak base up here. And as we add acid, we're going to see what happens to the pH. Now, it essentially is the flip of what we had when we had a strong base, weak acid. We're just starting up high and going down low. And here's our equivalence point again. This is the point where the moles of acid equal the moles of base. A little bit of a different wording to the question this time. We're not going to have like various points along the titration. It says, what is the pH at the equivalence point when 50.0 milliliters of 0.100 molar ammonia is titrated with 0.100 molar hydrochloric acid? So the hydrochloric acid is the strong acid. The ammonia is the weak base. So we want to write our reaction first. Okay, so the NH3, there's our ammonia. Remember that because hydrochloric acid is a strong acid, it's going to break up into hydrogen ions and the chloride ions. The chloride ions are spectators. The hydrogen ions are going to link up with water molecules and make hydronium. And we know that that hydrogen ion goes from the acid to the base. So we're going to produce ammonium ions and water as our products. And because strong acid is one of the reactants, the reaction is going to go to completion. All right, we want to get to the equivalence point. Well, we know the molarity and the volume for the base. If we know those two things, we can calculate the moles of our base. Now, it doesn't tell us the volume of the acid, but it tells us we're at the equivalence point. Well, at definition, equivalence point means the moles of the base equal the moles of the acid. So that must mean we've got 5.00 times 10 to the minus 3 moles of acid to completely react with our moles of weak base. So it didn't give us this information, but we can figure that out. And they happen to be the same numbers. They don't have to be. So all of our base is reacted. All of our acid is reacted at our equivalence point. But we're going to have ammonium ions left in the solution. Now, we can't figure out the pH directly from this number because the ammonium ions, well, that's not hydronium or hydroxide. So we have to figure out what happens to the ammonium ions in water. Okay, the ammonium ions are going to act like an acid. They're going to donate their proton to the water, and we're going to produce ammonia and hydronium. Well, that's what we need to figure out the pH. Now, this is moles of ammonium. We need molarity. So we're going to take the volume or the moles of the ammonium ion and divide it by the total volume, which was 50 milliliters plus 50 milliliters. So here's the molarity of the ammonium ion. A little bit of it is going to react. We're going to get X amount of ammonia and X amount of hydronium. I'm going to give you this. You'd look it up. The Kb for ammonia is 1.8 times 10 to the minus 5. The Ka for ammonium is 5.6 times 10 to the minus 10. So now we're at the point where we're looking at just a weak acid equilibrium. So here's your Ka. Here are your products. Here's your reactants. Set up your equilibrium. Solve for X. X is the hydronium ion. You can calculate what the pH of the solution is going to be. All right, so I'm getting 5.3 times 10 to the minus 6 for the hydronium ion. So 5.275 for my pH. Last thing we need to kind of talk about in this chapter is a little bit about indicators. So acid-base indicators are just substances that we can add to a solution, and they change colors depending on what the hydronium ion is. So as an example, we kind of looked at this before. Methylene or methyl orange changes colors around here. Litmus changes colors around here. Phenolphthalein, which you had in your lab, changes colors up around here. And no way do you need to know this. But if you look, there's a huge span of indicators that we can use, and they change colors depending on what the pH is. So if you've ever tested the pH in your pool or in a fish tank, okay, and you have those little strips, the strips are kind of soaked with, one of these indicators so that you can figure out what the pH of that particular solution is.